Alright guys, happy Friday. Questions while we got a minute. Questions about the lab report. Hydrates, acetal, imines, enamines, cyanohydrins, Wolff-Kishner, reductive amination, Strecker synthesis. Mark?
Is the lab report going to be due right after we come back?
When you come to lab.
Oh.
When you come to lab the week. And when you come to lab next time, we'll be doing what reaction? Vinick reaction. Spelled with a W, pronounced with a V. Vinick. German. George Vinick. Won Nobel Prize in 1979. Okay. Questions?
So, what was the reference with the batch brightness rule? The only thing I can tell is something close to pulp.
Something what?
Close to pulp fixture.
No, well, first of all, it's quite stupid. Second off, it's from CSI Miami. You remember Horatio Kane?
Yeah.
There was a person in the lab, something Wolf, and he would always go, "That's right, Mr. Wolf." And then it would go, then the Who song would come on. Before we get going, we have to update the, we have additional nomenclature we need to look at. Document camera. This compound right here, it's a unique compound. We need to know the name of this guy. Anybody know the name of that one? Penguinone. Yes, it is.
Wow.
It's penguinone. Add that one to your nomenclature list. Thanks to Mena for finding that jewel.
Oh, it's not good.
No, it's real. Look it up on Wikipedia. Okay, I think we need to make meth today. Hydrozones, oxenes, DNP tests, reductive amination. Okay, what's wrong with this reaction right here? We can try to combine everything. Allyl ketone reacts with primary amine to make imine. This is a reducing agent. We can reduce it, potentially get that product, but it doesn't work. Why does it not work? This doesn't work because the H- source will reduce the ketone, and you'll just end up with the alcohol. You can't combine everything with sodium borohydride. It'll reduce your aldehyde or ketone. You can do this separately like you did in lab. You can first make the imine. Everybody made an imine in lab? Then you can come in with sodium borohydride and reduce it. But you can't do it all together with sodium borohydride. You can do it all together with hydrogen and a catalyst. Well, hydrogen is hard to deal with. It's a gas. You have to have a tank. Closed apparatus. An alternative to sodium borohydride is sodium cyanoborohydride. If you use it, you can do it all together. That will not reduce your starting ketone. You won't do anything to the ketone. You get your imine made. It's not isolated, but then this is reduced with sodium cyanoborohydride. We got a B with 3 H's and a cyano group. That's a minus. This is not as reactive as sodium borohydride. If this is an H, if it's 4 H's, it's more reactive. Why is this less reactive? Because of the withdrawing group, the boron is not as mad. The boron's like, I'm minus, yeah, but I've got this cyano group that's pulling electrons away, so I'm not that minus. So I'm not as eager to kick off an H minus, so I'm not as strong as a hydride source. There's other reasons for why it doesn't reduce this, but that's a good thing to consider. So all together now we can use sodium cyanoborohydride, where you cannot use that. Make sense? Sodium cyanoborohydride is very useful for this particular purpose. So we can predict products. Okay, we have an amine aldehyde ketone reducing agent. This looks like reductive amination. It don't look like anything else. What's the product? Well, we have first the imine, double bond to the carbon. Carbon has a that and an H. There's your imine, right? And then this gets reduced, basically 2 H's to each one. Mechanism, H minus comes in here, electrons here, and then this picks up an H from, there got to be some proton solvents. Usually these are like ethanol or appropriate workup. And that would give what? And with an H and that. So this becomes an ethyl. When you add an H here, that becomes an ethyl. H there. So what did we do overall? We put an ethyl group on the nitrogen. That's what we did overall. We alkylated the nitrogen. Not directly, but indirectly. Indirect alkylation, the general process is called what? Reductive amination. Because really we aminated this carbon in a reductive process along the way. Products of the other ones. Get this amine here. Yeah? Hopefully you have these already on your paper. And this one here. How about this third one here? What's going on here? We've only got one molecule on the left. But that one molecule contains an amine and a ketone. So what could happen here? An intramolecular reaction. This could react here, and eventually you get the imine. What size ring are we making over here? 1, 2, 3, 4, 5, 6. 1, 2, 3, 5, 6. There's nitrogen here. It's now double bonded to what used to be the carbonyl carbon, and there's a methyl there. That used to be a carbonyl carbon, right? Imine. Bonds with carbonyl carbon, loses water. And then when this gets reduced, what do we get? When you reduce the imine. And methyl. So that's a intramolecular version of the reductive amination. How do these look? Questions about these? What's the difficulty here? I don't think there should be much difficulty if you sit down and see, okay, what's going on here, what's bonding to what, what's an imine, Show the imine. After you show the imine, the double bond gets reduced. You add an H to the nitrogen and the carbon, you get your amine. Okay, what if we go backwards here? Let's see here. We have some compounds here. This is phenylpropanolamine, PPA. If you buy like no-dose pills, it's either caffeine or PPA. Basically, it's a stimulant, phenylpropanolamine. Diet pills contain phenylpropanolamine. Make you all like, let's go. There you go. Simple molecule does lots of the neurological properties. If you add a methyl to phenylpropanolamine, you get Sudafed, decongestant. If you take phenylpropanolamine and remove the oxygen, you could say remove the OH, but actually you remove the OH and add an H. The only difference is you remove oxygen. You have amphetamine. No OH group. If you put a methyl on the nitrogen, what do you have? Methamphetamine. The two at the top are legal, the two at the bottom are not. Amphetamine is sold as like Adderall or some type of mild stimulant drug. Meth is typically not sold in the drugstore. But Sudafed is, and lots of people like to buy Sudafed and remove the oxygen, remove the OH group, and convert it to methamphetamine. That's why Sudafed you can no longer buy 100 boxes at a time, like you could back in the 80s. So that's the old meth lab approach. Breaking Bad, they use like phosphorus to remove the oxygen. Probably made phosphinic acid. If you remember phosphinic acid, it's reducing the acid. Reduce off the OH with an H. Methamphetamine. Question though. Provide two different syntheses of meth with both using a reductive amination approach. The approach we just used. How would you make methamphetamine using this? So what is a reductive amination? You make an imine and then you reduce it to the amine. What components do you use to make the imine? It's like an aldehyde ketone and an amine itself. And that amine is going to be eventually converted to another amine, but the other amine will have an alkyl group added. So eventually we're going to add an alkyl group, okay? So, what amine do you want to start with to make methamphetamine? You could just start here. What would you react it with to get this in a reductive amination sequence? First we want to make an imine. The imine, how many carbons do we want the imine to contain? 1. We're adding one carbon to the nitrogen. So we need a carbonyl. How many other carbons? None. So what else is on this carbon? Yes, H's. That's formaldehyde. It's like a double aldehyde. And if these two reacted, could you make an imine? Yeah, what would you get? You would get boom, 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 nitrogen. This would be then what? Tell me what it would be. What's an imine? Double bond to carbon? Sure, double bond to carbon. There's the carbon. What's on the carbon? 2 H's. Minus water. Okay, we've done that about 7 to 9 times, probably more like 12. Okay? You got to get that. This is our imine. What do we need to do to this imine to now get final product? We need to add an H here and an H here. What do you want to do that with? Now, if you do it separately, you can use sodium borohydride. You can do H2 with palladium or carbon or something. Some type of reducing agent. There you go. Amphetamine reacted with, basically up here, we'll show it all together now. H2 palladium, palladium on carbon. Boom. That's a reductive amination. Amphetamine to methamphetamine. Make sense? How about another approach, though? Another reductive amination. What other aldehyde or ketone and amine could you start with? Instead of adding the methyl to this amine, what else could we do? What if we add this thing to that amine? How could we do that? Well, because we often put the biggest reagent on the left, how about if I put this ketone? What do we want to react this ketone with to get that molecule over there? NH2, CH2? NH2CH3, methylamine. Methylamine, what else do you want to include in this? Sodium cyanoborohydride or hydrogen. What do you first get? You first get the imine, nitrogen bonded to the carbon, double bond, after you lose water. But what happens to the imine? That's the same imine as, no, it's not the same imine, it's different. It's imine on the other side. You reduce this, what do you get? You get product. So it's two different ways. It's kind of like when you make an ether. You could have the alkoxide and the alkyl halide, or you can have this alkoxide and this alkyl halide. Now actually, if you watched Breaking Bad 5 years ago, they started, I think, making that approach, but then they started making this approach. And at some point, the young guy was stealing a tank of something from a company. What was he stealing? Stealing what? He wasn't stealing meth, he was making meth. What was he stealing? It was a tank of something. Methylamine. Wasn't he stealing methylamine? Yeah. So they could do this. I don't know where they got the reducing agent or what they were using, but I remember, I think at one time he was stealing a tank of methylamine from a warehouse. Because they like this approach better for some reason. Okay. F. Reductive amination is very powerful because the two components you bring together can be huge. I mean, you can have a huge ketone, you can have a huge amine, and you can bring them together and have a doubly huge molecule. F, synthesis of aldehydes and ketones from nitriles. I'm going to not say this and pretend it's not there. Okay? Divol H, what is that? Hydride source, right? This H minus source. We showed this reaction at the very end of test 3. This can add to the carbon electrons over. You get R carbon with an H, double bond N, and that's minus. Nucleophilic addition of hydride to nitrile. That's nothing new. Now, anytime you use diball H, it only adds once. I'm not going to add any more. First step is over. This is just going to sit here. Now let's throw in some aqueous acid. What's going to happen to this when we throw in aqueous acid? H plus and water. Now that's going to protonate, because that's an anion. We're throwing in acid, and we get that there. And what is that right there? Functional group. Abdul? Imine. Now we got acid and water, and we can add a lot of water here. What happens to imines if you treat them with acid and water? It hydrolyzes. It reverses. When we made imine, we said it was reversible. How do you reverse it? You add water and it goes the other way. Okay? When you add the acid and the water, what do you get? You get R. That's a carbon there, right? Plus what? Plus NH3. You get the aldehyde ketone in the amine. You add oxygen here, 2 H's here. That's NH3, but we're under acidic conditions, so how is NH3 going to exist? We protonated. And lo and behold, what do you have there? You have an aldehyde via imine hydrolysis. At this point, we're just in the kitchen baking whatever we want, because we've seen all this chemistry. We're just putting it together and say, hey, this is a neat way to make an aldehyde from a nitro. You can do the same thing with a Grignard. Now, Grignards usually add multiple times to acid chlorides and esters and stuff. But Grignards will only add once to nitrile. That's something new. What do we get here if we add this? It's the same thing, except here the nucleophile is what? Whatever the R group here is. So this is minus, right? Add here. You get R, C, phenyl, anion. When we add the aqueous acid, what are we going to get? We'll first protonate and get the imine. But then the imine is hydrolyzed to what? The aldehyde or ketone. This happens to be a ketone because there's two R groups, R and whatever the Grignard was, ketone. It's the same exact process, except you have an R group from your aldehyde instead of an H. Questions about this? Just a neat way to make an aldehyde or ketone from a nitron. Adding a nucleophile and hydrolyzing the imine. Lots of applications of imines. Here's a couple of reactions. The top one is a little bit unique. I included it because I've actually done that reaction before. And then the one below. Show the products of these two. Everybody get a handout today? Are there extras somewhere? You get the dialdehyde up there. John?
If you didn't use excess, would it be selective toward the left side?
Why towards the left side?
Just because the oxygen is donating, it would be less proportional flow. Right.
It's donating to what?
Toward the cyanide.
How's it donating toward the cyanide? I thought you were going to say resonance. Then the question is, well, could you show a resonance structure of it donating to the cyanide? Can't show it. I don't know, I don't see anything that would clearly show preference. You could be research. I don't see anything. The oxygen is really just pooling here. You cannot show resonance of this lone pair into the nitrile, because if you show resonance here, what are you going to do here? There's nothing to do. You have to move these out here. You cannot move these electrons into the nitrile. How about down here? It's all the same thing. Okay, what does this do with magnesium? Make Grignard, phenyl magnesium bromide. What will Grignard do with the nitrile? And we end up with CH3, C with a phenyl, double bond N. It's going to be a minus, but then when we add the acid, that picks up an H. And so we have a couple of reactions here to get to this point, and then we hydrolyze it, and what do we get? We get that there, which, by the way, is known as what? Test 3 was only 2 weeks ago. What was it known as? I'm sorry, that was test 2. Acetophenone. Acetophenone. Provide a synthesis of the following ketones from benzene using this new route. And also using the organocuprate route. Remember organocuparates? What was that reaction good for? Organocuprates react with acid chlorides to give ketones. Great way to make a ketone. Here's a ketone. Great way to make that ketone. But also give a route using this new route, because this we just also made a ketone. You can react with Grignard with a nitrile to give a ketone. from benzene. Please work on that for next time. A couple miscellaneous things here in the white handout. Metabolism. Let's take a quick second to look through these. Anybody have any questions about this one? There, questions about the questions? Anybody have a question about this one? Alright, ketones. Anybody have questions about spectroscopy? There's several comprehensive spec problems in the workbook. There will be a comprehensive spec problem on the final test, just like on test 1 and 2. We do have chemical tests. We've already seen one, the DNP test. We'll actually see 2 more in the purple handout. Maybe it's only 1 more. We saw hemiacetal form, acetal. Okay, this is what's written at G. A lot of drugs in the body are metabolized by oxidative dealkylation of amines. You take a pharmacology class in med school, dental school or something, you'll look at metabolism of drugs probably a little bit. Oxidative dealkylation of amines. For example, amphetamine. Amphetamine in the body is converted to this ketone. And you generate the amine. This looks like the reverse of a reductive amination. So these two could react. To get that, you would have to have a reduction to get back there. Well, see, the body is what? The body is a lean, mean, oxidizing machine. It will oxidize many things. The body will actually oxidize this to the imine. You know, we were reducing it with like sodium borohydride. Well, your body will go the other way. Imine, and then what happens to imines in the presence of aqueous acid? Because your body has lots of aqueous, and there's plenty of acid catalyst around in your body. What happens to imines? All aldehyde ketone derivatives can be hydrolyzed back to the aldehyde or ketone, and when you do that, you get the ketone, the amine is released. That may be NH3 or it may be NH4+. And so there you go. That's how you would, your body does this, and that's why such compounds can be detected in the urine. It's good old organic chemistry. We're just going backwards there. If we look at a bigger drug, same thing. Imipramine, tricyclic antidepressant. If you oxidize here, make the imine, it's kind of a unique imine because the nitrogen can't go neutral. You remove the 2 H's. But still, you hydrolyze this with water. You liberate the aldehyde ketone in the amine, so what do you get? You liberate the amine, you get this. What else do you get? Somebody said it. What's it called? We saw it a little bit over 20 minutes ago. Formaldehyde, yes. We're just going backwards. Earlier we used formaldehyde to put a methyl on amphetamine. Well, if you take a methyl off, you'll generate the amine in formaldehyde. Well, this was an original drug. They realized that this was happening and this was forming in the body. At some point somebody actually tested this for antidepressant activities. And it's actually more active as an antidepressant drug than the original. So you know what they then started doing? They then just started giving this as the drug. That's imipramine. This is called dizipramine. The DE kind of from dealkylated or demethylated. Actually, as I read it here, the original drug is actually not even active. And originally they didn't know that. It's only active once the body removes the methyl, and then it's an active drug. Once I realized that, they then just started giving the active drug as the main one. Whenever a compound that you take is not the active form, it's called a prodrug. Lots of drugs out there are actually prodrugs. The molecule that you originally take is not the active form. But the expectation is your body will convert it to the active form by metabolism, either enzymatic or just plain hydrolysis. Okay. Anybody like to see? Vision. This is actually from your Klein textbook. I think I actually mentioned this already. Let's see what else is in here. There was a reductive navigation, but I think I took it out. There's lots of miscellaneous stuff in here. I don't want to overload you, but it is lots of good miscellaneous examples of the stuff we're doing. Okay, well, the next for two is in both this handout. By the way, I mentioned this before, but amines are called what in biochemistry? Shift bases. Okay. When you get to biochemistry and your biochemistry professor says shift base, I want you to look at them and say, I know the lingo. I'm with you. Keep going. Tell me more. All right. Okay, miscellaneous reaction. Vinick. Germans pronounce it Vinick. The Vinick is actually on the handout here, written handout. George Vinick. Can I get a vowel? Won Nobel Prize in 1979. He actually shared Nobel Prize with H.C. Brown. 1979. What did H.C. Brown develop? Sodium borohydride. H.C. Brown was big into boron chemistry back in the 1940s and 50s, doing things with like BH3. And he discovered sodium borohydride, probably one of the top 10 discoveries of the 20th century in chemistry. Sodium borohydride, very versatile, very easy to use because it's not highly reactive like LAH. Before sodium borohydride, everything had to be done with hydrogen gas. Okay, sodium borohydride really changed and helped that, made it more versatile. You know, 100 years ago, only maybe one lab in Georgia or 200 years ago had hydrogen gas available. Just hard to use. You have a tank and special apparatus. Okay, Vinick. What does the Vinick do? It converts a carbonyl to an alkene. So we don't replace the oxygen with a nitrogen. What are we replacing the oxygen with? Carbon. All right. Here's an example of a Vinick reaction. Aldehyde ketone. We react with this funny looking thing. It's a double bond to phosphorus. We get the alkene plus triphenylphosphine oxide. Basically, it's like you're dancing and you switch partners. Okay? See here, the carbon is double bonded to oxygen, but now it's double bonded to carbon. And here, the phosphorus is double bonded to carbon, but now it's double bonded to oxygen. See, they switch it up. But of course, we don't just learn things like that. We need to look at the mechanism and be able to work with the reaction, see the reactivity of the reagents, and how does this happen. So what is this thing? First off, it's called a phosphorus Iligan. What is an Iligan? I thought you'd ask. It's a net neutral 1,2 dicharged compound. It's a compound that has adjacent charges, but it's net neutral. So thus, if it's net neutral, the two charges are going to be what? Both positive? Of course not. One's positive and one's negative. Two charges, but it's net neutral. That's what an Iligan is. And there's your Iligan. Right here. Also known as a Vinick reagent. It's a novel name. Now, this is a Lewis structure for, okay, the phosphorus has 8 electrons around it. The carbon has 8 electrons around it. You do see the H there, right? Okay. It's a good Lewis structure if we go back to week 1 of organic 1. But phosphorus can expand its octet. It's below row 2. It's got d orbitals. We can move these electrons in here. And what does that give? It gives this. And that's a resonance structure. And so let's just use a resonance arrow. Okay? And what is this? That is what I showed there. Okay? So there's 2 different resonance forms that can be used. This form is good to say, okay, or if we sort of what's replacing what, let's go back up here. Basically, I'm going to get rid of the oxygen, and I'm going to get rid of that. This double bond portion, if I could just take that half and combine it with that half, I get the product. Right? If I could just take this and put it here, you see what I mean? Because it's double bond to carbon with a methyl. It's now double bond to carbon with a methyl. This resonance structure is sort of good to just see what's being put together. But this resonance structure is your best one for doing your mechanism. Now what's the true structure? True structure is somewhere in between, right? Both forms have. Which one's major, which one's minor? Well, some people would say this one because there's no charge separation. Well, if there's no charge, then is it an Iligan? Well, that's because there is some charge. It's somewhere in between. Some people don't like this because they don't like showing more than 8 electrons around phosphorus, and they like to stick to octets. Okay, this is better for mechanism. Let's use that for mechanism. We're going to react that with acetophenone. See, this is a neutral. You can weigh this out. You don't have to react it with base yet. We'll see how to form this. Okay, we have a nucleophile. Nucleophiles like to add the carbonyls. Boom. Electrons up. What does that give? Now I'm going to draw this in a very, very precise orientation. Phenyl. There's the phenyl on the methyl. What came in? This is the bond we just made. Something attacked electrons to the oxygen. What came in? Carbon. Carbon's got a methyl. and it's got a phosphorus, and the phosphorus has 3 phenyls. And that's a plus charge still. Okay? All we did there was do a nucleophilic addition to a carbonyl. Now at this point, oxygen really loves phosphorus. Okay? There's certain elements on the periodic table that really love each other, oxygen and phosphorus. Really, lots of things love oxygen. Oxygen and boron. Fluorine. What does fluorine really love? Silicon. That's why HF will dissolve glass and stuff, because silicon dioxide. Fluorine, silicon, love each other. Loving means what? It means it makes a very strong bond, very exothermic, very good thermodynamics. There's other things. Okay? Oxygen and phosphorus really love each other. Also, pluses and minuses really like each other. What can happen here? Can this be attracted here? Yeah. Can the phosphorus accept more electrons? It's already got 8. Sure. Remember, how did it accept these with the resonance structure? Okay? It has empty d orbitals. What does that give? Gives that. The oxygen is now neutral because the lone pair made a bond. Okay. What's the charge of the phosphorus? It's also neutral. Because if you count electrons, each bond is 1 electron. 1, 2, 3, 4, 5. Phosphorus is group 5 under nitrogen. See, now everything's neutral.
Would the oxygen bond with phosphorus consider resonance? Or would it,
Is that resonance?
yeah.
No, that's not resonance. We just made a sigma bond. When you do resonance, you're only making pi bonds. Not resonance. Despite what some textbooks may want to show you because they don't know what they're talking about. Okay, that's a 4-membered ring over there. Why would you want to make a 4-membered ring with 90-degree bond angles? Because oxygen loves phosphorus. And pluses like minuses. Okay. Well, at this point, we undergo an electron reorganization because oxygen really likes phosphorus. This oxygen wants to bond that phosphorus as much as possible. How many bonds do we want to make with that phosphorus? There's your product up there, 2. These electrons then bond again. But at this point, something has to go because phosphorus can't make 6 bonds. So these electrons have to leave. Well, these go up here and make pi bond up here. Well, something has to leave here. Because carbon can't make pi bonds. Well, these just come off and go back on the oxygen as a lone pair. This is just a cyclic rearrangement of electrons. It's not resonance. And there's a chapter in your textbook that talks about pericyclic reactions. Reactions that have cyclic transition states. Diels-Alder is an example of a pericyclic reaction. That's 2 different molecules coming together. Okay? Didn't we have something decomposed like this when we did oxidation of something? When we did oxidation of diols, we made like an osmate ester, and then it sort of rearranged. It's sort of something like that. What does all this give? Final products. Let's look at it. We got, what are we doing right here? Pi bond between the 2 carbons. What else is on this carbon? The methyl. And the rest is gone. Then below we have phosphorus with 3 phenyls. what are we doing here? It's going to be a phosphorus oxygen double bond. That lone pair was used. There's only one lone pair, but what is this doing? This is coming on the oxygen as a lone pair, so ultimately we end up with how many lone pairs on oxygen? 2, as needed. There's your 2 products. That's nothing new because that's what's shown right up there. Now, the alkene can be E or Z. I'm not sure which one I drew there. It's a pretty ugly bond angle, yeah? That's just product. E or Z, that's one of the limitations of Vinick. In certain cases, you can give preference for E or Z. And then you make triphenylphosphanoxide, which is purified out. Alkene. This has been huge. I think there's a handout that shows a drug synthesis that includes a couple of Vinick reactions. One Nobel Prize. Let's see what else is here. Down below, look at how you make your Iligan reagent. These have to be made. Now in lab, we will use this already made. You can buy these like that. You can make them. We need to know how to make them. Down here is how you make them. Please look at how you make them. We're out of time. Please also look on the next page, the applications, and then this drug synthesis that shows a Vinick. Shows 2 Vinick reactions. When we come back from the break, we'll be doing a Vinick reaction in lab. It's in the workbook, of course. Please have a safe break. See some of you this afternoon.
Give it.